So, in this module, you shall be able to know about general introduction and mathematical details of mole ratio method. You will understand the limitations of Turner and Anderson's method for metal-ligand ratio and will learn about the details and advantage of Yatsimirskii method. Introduction. Yeo and Jones developed the mole ratio method for inferring the composition of metal complexes from spectrophotometric data in the solution. The fundamentals of this method includes a general metal and ligand reaction of the type where metal M reacts with n moles of ligand to form MLN complex. In other words, it is an alternative to the continuous variation method for stoichiometry determination in metal-ligand complexes. In this method, the moles of one reactant, which is generally the metal amount, is kept constant, whereas the moles of the other reactant are changed. When a ligand is added to the metal solution, the absorbance is observed at a wavelength of absorption point of the resulting complex. In this method, a plot between absorbance and mole ratio of constituent L to the component M, wherein the concentration of the metal M remains constant, is drawn. If the reaction product is poorly dissociated, the absorbance plot rises sharply in the form of a straight line towards mole ratio axis and thereafter steeply breaks with a constant absorbance at the mole ratio of metal ligand in the complex. The break in the curve suggests that the mole ratio, that is L by M in the product, if the concentration of metal M is kept steady and ligand L concentration is changed. On the other hand, the mole ratio plot does not exhibit sharp break, rather only a slow change of the slope is obtained with a constant absorbance at high mole ratios if the complex is highly dissociated. If the solution of high ionic strength are investigated, then the breaks in the curves frequently become sharper. It is noteworthy that the mole ratio method has a limitation where reaction involves formation of more than one complex under analogous conditions. Notably, the mole ratio method presents discrete advantages over the continuous variation method for the complex systems that entail high ligand metal ratio. For example, the ratio ligand to metal is 5:1 or still higher. Generally, if the ligand L reacts with metal M to form n successive complexes, then the ith complex is denoted as ML with the subscript I, commonly known as MLI. Its concentration is designated as the concentration of MLI. Whereas, for a reaction of the type where metal M reacts with n-ith ligand L to form the complex MLNI, the dissociation constant K is given as the concentration of the product metal M to ligand L raised to the power Ni divided by the concentration of metal Lni to the power N, where N is actually the total number of ligands and I is the ith step of the reaction. Let us now study about the mole ratio method. This is an approximate method and it can be applied to only those systems in which only one type of equilibrium or single complex formation takes place. In this method, the fraction of the complex units is determined by the variation point obtained in the plot of optical absorption versus the mole ratio of the reactants. The mole ratio method is applicable only for a strong complex. The different type of plot is obtained for various stoichiometries. For example, 1:1, 1:2 and 2:1 corresponding to the mole fraction of either of metal or the ligand. The diagrammatic elaborations shown in figure 1a and b demonstrate the representative results. In figure A, we can see in 1:1 metal ligand Ml type of complex, the mole ratio plot, the absorbance is observed at the wavelength point where merely the complex absorbs. In figure 1b, in 1:2 metal ligand Ml2 type complex, mole ratio plot wherein the absorbance and the wavelength of all three existing species, that is the metal, the ligand and the complex is same. In other words, these three species absorb at the same wavelength. Conversely, a mole ratio plot for 2:1 metal ligand, that is M2L type binuclear complex, is quite similar to the 1:2 Ml2 type of complex, with only difference in metal and ligand units. This can be clearly shown in figure 1b. The mole ratio plot can also be obtained for stepwise complex formation like Ml complex, Ml2 complex shown in figure 2b. One shows the mole ratio plot for the formation of metal ligand complex with increasing mole fraction of ligand, 1:1 metal ligand ratio and 1:2 metal ligand ratio. The figure 2 represents the mole ratio plot for the formation of A 1:2 complex with excess of ligand and B the stepwise complex formation with increasing the mole fraction of the ligand. It is quite clear from figure 2b that absorbance of the complex continuously increases with increasing the ligand units. The absorbance is proportional to the mole fraction of ligand. Thus, in octahedral complexes, the absorbance follows this order: Ml6 complex greater than Ml5, the absorbance of this is still greater than that for Ml4 complex, then for Ml3, then for Ml2 and finally for Ml metal ligand bonding. Now here to specify that L is a monodentate ligand, say for example ammonia. Therefore, the plot obtained by drawing a tangent at mole fraction x is equal to 0 and at a point where it becomes optimum, that is for here it is Ml6 in the above mentioned system. The absorption first increases till the saturation of complex and then it becomes constant. This constant is represented by the point C. At this point C, the maximum possible complex formation takes place. The stoichiometry of metal and ligand can be clearly known by the x-axis, and this x-axis is the mole fraction axis. In mole ratio method, the total concentration of metal or ligand analytes is kept constant. However, in Jobs method, the sum of the concentration of metal and ligand is kept constant, and the absorption point that is measured is the wavelength where the complex absorbs. But neither of the metal or ligand absorbs at this wavelength. In general, the mole ratio method is appropriate for the determination of composition in high ratio complexes. In the continuous variation method, the complexes having the mole ratios of 4:1, 5:1 and 6:1, the Absicca values found correspondingly are 0.8, 0.833 and 0.857. The outline of mole ratio method is applicable to series of closely spaced wavelengths. Therefore, the mole ratio method offers better positive signaling whether spectrophotometrically apparent complexes are present or absent. Let us now study about another method, Turner and Anderson's method. Turner and Anderson's method is also known as matching absorbance method and applicable for determination of stability constants of the complexes. A series of solutions prepared exhibit same absorbance despite difference in the concentration of ligand and metal. Therefore, two different solutions with different metal ligand ratios are determined at the strong absorption wavelength of the complex. Further, the concentrated solution is diluted to make the absorbance of both the solutions same. Consider for this reaction where the metal M reacts with n number of moles of ligand to form the complex MLN. The equilibrium constant for this above reaction is given as K is equal to the concentration of the complex MLN divided by the product of the concentration of metal M and the concentration of ligand to the power n. Now, we know that the concentration of metal M is equal to the total metal concentration Tm minus the concentration of MLN. Also, the concentration of the ligand L is equal to TL minus N to the concentration of metal ligand complex MLN. Substituting the above values, we arrive at a situation where the constant K is given by this equation, where Tm and TL are the total concentration of metal and ligand respectively. When Tm and TL values are different, but absorption and K is same. In this case, the value of K is represented by this equation. Now, the solution of the above equations where the value of Tm, TL and MLN are known, then we can find out the value of the stability constant K. Let us now study about the limitations of Turner and Anderson's method. This method is applicable to only one type of equilibria into the solution. This is applicable for moderately stable complexes. Let us now study about another method, Yatsimirskii method. This is a general method which is useful to study the system in which more than one complex absorbs. If A is the absorbance of the system, then according to Lambert's Beer law, absorbance A is equal to epsilon CL. Here, as you can see, L is the optical path length, C is the concentration of the absorbing species. Here the units are expressed in moles per liter, and epsilon is the extension coefficient. On rearranging, we see that absorbance A by epsilon is equal to CL. Since absorption is an additive property, so for the system where metal M reacts with ligand L to form Ml, the individual value of epsilon for Ml is shown in the equation. Further, for the kind of the reaction where metal M reacts with 2 moles of ligand to form Ml2. So, for this equation, the value of epsilon given as epsilon 2 for the complex Ml2 is given as epsilon 2 into beta 2 multiplied by the metal M concentration multiplied by the ligand L concentration raised to the power 2. Similarly, applying the same concept for the type of complex where metal M reacts with 3 moles of ligand to form Ml3. So, similarly for this reaction, epsilon 3 is equal to epsilon 3 beta 3 metal M concentration and ligand L concentration raised to the power 3. Each complex will have separate molar extension coefficient epsilon. So, mathematically it is shown A upon L is equal to epsilon 1 C1 plus epsilon 2 C2 and so on. Putting the values in this equation, we arrive at an equation where we say A upon L is equal to epsilon 1 beta 1 metal M concentration, metal L concentration plus epsilon 2 beta 2 metal M concentration, L concentration raised to the power 2 and so on. Dividing both sides by total metal concentration Tm, we arrive at mean molar extension coefficient, which is represented by epsilon bar. Now, this epsilon bar is equal to A divided by total metal concentration into L. And when substituting the individual values of Tm into here, we arrive at this equation. And it can be seen from the equation that the mean molar extension coefficient epsilon bar is independent of the total metal concentration Tm, but certainly it depends upon the concentration A for a particular system. So, if a series of solutions have same absorbance even by differing Tm values, they must have the same value of ligand L concentration. So, also for N bar, alpha C and phi. When a graph is plotted between TL and Tm, we introduce a new function f1, which is given by the ratio of epsilon bar by the ligand L concentration. Substituting the values of epsilon bar and the ligand concentration, we arrive at this equation. Now, applying the limit ligand concentration approaching to L, this f1 function, f1 is equal to summation beta 1. Here we introduce another function f2, which is given as f1 minus epsilon 1 beta 1 divided by the ligand concentration. On substituting the different values of F1, beta 1 and ligand concentration, we arrive at this equation. Applying the limits when concentration of A approaches to 0 to function F2, this is represented by this equation, limit concentration A approaching to 0, F2 is equal to epsilon 2 beta 2 minus epsilon 1 beta 1 square. Now, considering the reverse of it, which is represented as summation bar, it is shown by this equation. Dividing this equation by L raised to the power n, we arrive at a function which is represented as psi 1. Applying limit to this function where concentration of A approaches to 0, this is given by epsilon n. Similarly, taking another function psi s, which is represented as psi 1 minus epsilon n divided by the ligand L concentration. Similarly to this equation, we can apply the limits when concentration A approaches to 0. This will be shown as epsilon n minus 1 minus epsilon n beta n minus 1 divided by beta n. Let us summarize what we have studied till now. In the mole ratio method, its mathematical, derivation, applicability and limitations have been described. The Turner and Anderson's method for metal-ligand ratio has been discussed along with its limitations. Yatsimirskii method, which is used specially for more than one complex system absorbed, its mathematical derivation has also been elaborated.